So let us resume our discussion for the special relativistic properties which we were discussing in the previous class, and let us try to see how do we go about from having Lorentz transformations to get good laws of physics under special relativistic transformations. So remember, in the previous class we have learned that in order to keep the speed of light same across all inertial frames, we are bound to have transformations between two different inertial frames moving with respect to velocity v with respect to each other through something called the Lorentz transformation. And we obtained the form of the Lorentz transformation through simple algebraic manipulations of constancy of the line element, which is dt square, c square dt square minus dx square dy square dz square. That should be the same for speed of light across all frames, and we ended up getting the set of Lorentz transformations. Now, that was the first premise or the first basic ingredient of the special relativistic properties which we had discussed in the previous class. We wanted to have two properties, that speed of light remains same in all inertial frame, which we have now achieved through Lorentz transformations. And now the second part of it is the laws of physics should remain invariant form in all inertial frames. We had previously learned that the Newton's law, which was the response of a particle or a system to application of a force, is not a constant anymore across all frames. It was a constant or invariant for all inertial frames if the frames were connected by Galilean transformations. But if the frames are connected by Lorentz transformations, this is no longer true. That the accelerations, which is defined as d2x upon dt square, is not same under Lorentz transformation across all inertial frames. So second law of Newton is not holding anymore. So similarly, here we want to get a good correct second law of Newton's analog, or a correct force law, as to say. So let us see why was that the acceleration as a response to application of a force was invariant under Galilean transformation, and let us see if some of the basic premise of that can be again translated into Lorentz transformations or not. So in the Newtonian regime, the force law was actually a vector equation. The force vector was equal to m times the acceleration vector, and therefore one can write a new vector, call it a y vector. A y vector which can be defined as f minus ma, and that was supposed to be 0 according to Newton's law, Newton's second law, and in all inertial frame this was supposed to be 0. That means what is being told, that this vector y, which is f minus ma, happens to be a null vector, a vector with 0 magnitude or a 0 vector. And we know that under spatial transformations, all with spatial transformations like rotations and whatnot, a null vector remains null. Therefore, under Galilean transformation, when we were doing that, what we were doing was just changing spatial coordinate, spatial labeling, new axis, which was just obtainable from a spatial transformation. But any spatial transformation cannot make a null vector a non-null. So therefore, in Newton's frame under Galilean transformation, this force law was being respected because it was a vector equation. Some vector was being equal to 0. Therefore, it was respected across all spatial transformations. Now, we have learned that Lorentz transformation is not only spatial, it has a temporal part as well. Time also changes. So only spatial transformation respecting vector should not be the principle which we should move along. One way would be to write down the force law in terms of space-time vectors. Space-time 4 vector it is called, as a null equation. Previously we had written down a null equation with respect to spatial vectors, and we were doing spatial transformations only, so everything was good. Now since we are forced to do a space-time transformations, we should rather look for space-time for vectors and actually space-time for vectors which are null, just like the case of Newton's law. So that is our guiding philosophy, that we will try to find out 4 vectors and write down force equations in a null form of those 4 vectors. In order to do that, we need to know what are the space-time 4 vectors. Okay, so the same question could be casted in spatial 3 dimensions as well. What are the spatial vectors? So in any dimensional space or space-time, more generally, vectors are defined as, vectors are those quantities which transform as the coordinate differentials. So dt, dx, dy, dz, these are the 4 coordinates in space-time. In spatial dimensions, only dx, dy, dz would have been 3 coordinate differentiable, but in space-time there are 4 coordinate differentiable, dt, dx, dy, dz. Collectively, they are given the name dx mu, where mu index runs from 0 to 3. It can take value 0, 1, 2, 3, where 0 is reserved for the temporal direction, 1 is reserved for the x direction, 2 is reserved for the y direction, and 3 is reserved for the z direction. Okay, so this would be, these are the coordinate differentials. Whatever transforms like a coordinate differentials will be a vector. For instance, if I define the coordinate differential and divide it by some scalar quantity which does not change under frame transformation, then this quantity dt upon d lambda, where lambda is a scalar, will also transform like dt, because d lambda does not transform at all. All it will transform will be through dt. Similarly, this quantity dx upon d lambda, all it will transform through would be via dx, and similarly for dy upon d lambda. So if lambdas are invariant, then dt upon d lambda, dx upon d lambda, dy upon d lambda, and dz upon d lambda are also transforming like coordinate differentials, and these can be defined as vectors. So I can define a 4-dimensional velocity, which is not the derivative of coordinate differential with respect to time. Previously, again, in Galilean transformation, we were doing exactly the same thing. We were saying that dx upon dt, dy upon dt, dz upon dt, where the velocities, because in the Galilean transformation, dt was a scalar, it was not changing under transformation. So similarly, in Lorentz transformation, so that dt is starting to change, so I cannot use dt in the denominator of the division. I should rather find out some scalar which does not change under coordinate transformation through Lorentz transformation, and that scalar's division or the rate of change of coordinates t, x, y, and z with respect to that invariant coordinate, invariant parameter, should be defined as a velocity. When I say invariant, it does not mean constant. I'm not saying that lambda should not change from a point, from time to time or something. Just like time was flowing in the Galilean transformation, it was not constant. Only that in different frames, they all agree that if one frame declares it value 5, all other frames declare it to value 5 as well. If one frame declares it to be value 6, all other frames will declare it to value 6. So similarly, in Lorentz transformation, we should find out a parameter whose value is universally agreed upon by all the inertial observers. So those things will be scalars. If I find such a scalar, which we will see an example soon, that scalar's further derivative, for example, I can take this v mu and take one more derivative with respect to lambda. So that would be something like d2x mu upon d lambda square. Again, the same thing, since v mu transforms like a vector and d upon d lambda is invariant, then this quantity is also a vector. So basic building block is whatever transform like coordinate differentials is a vector, and coordinate differentials derivatives with respect to invariant quantities are also transforming like coordinate differentials themselves. So therefore all those things are vectors. So we have a velocity for vector v mu, which is the first derivative of the coordinates with respect to some invariant scalar. Similarly, the second derivative of the coordinate differential, which is the first derivative of the velocity, is the acceleration for vector. Okay. So in that sense, if I can define an acceleration for vector, which is d2x upon x mu upon d lambda square, then I can write down a force law, which is a generalization of the previous force law, like this, that for vector f mu, some 4 force space-time force, previously only spatial force which we were dealing about, should be equal to m times the space-time acceleration. Previously we were writing only the spatial acceleration. If we could write such a law, then this law, this equal to 0, again will respect the conditions like before. In one frame, if the 4 vector r mu is 0, in all other frames which are inertially connected to it, a 0 vector will remain 0. Okay, so that is the idea, that one needs to find out a vector laws, and in order to get vector laws or invariant laws, that those things would be physically meaningful. So let us try to see what kind of invariant quantities which we can come about. So one invariant quantity we already know in this game is speed of light. That does not change from frame to frame. But too bad we cannot use it as a lambda, because lambdas needs to be varying as well. Not only c, speed of light is invariant across all frame, it is constant as well, that it does not change its value ever. We do not want that. We want some parameter which changes value, but when it changes value, the new value is also universally agreed upon by all inertial frames. The previous value was also agreed upon all inertial frames, and so on. So we do not want constants, we want invariants. So let us try to find out what kind of invariants which we can get from Lorentz transformations. So for that, I will just write down the Lorentz transformation one more time, which we had previously written, that c dt prime square, c dt prime is some combination of previous c dt and previous dx, and dx prime is also some combination of previous c dt and previous dx. So together, the two equations here, which here are given here in the box form, can be rewritten in a matrix notation. So I can write down a 2 cross 2 matrix which is connecting the old time and old spatial x to new time and new spatial x and their differentials. Similarly, if I expand the domain to 4 dimensions, 3 plus 1 dimension, if I am moving along only x direction, nothing is happening along y and z direction. So dy prime should remain dy and dz prime should remain dz. That means they are connected by some identity matrix, while t and x's are getting mixed, so they are connected by some non-trivial matrix, which is here. So in 3 plus 1 dimension, this block diagonal matrix is appearing as a matrix of transformation, and that we give a name lambda. So coordinate differentials or vectors transform like lambda. Okay, this is the rule, that coordinate differential will transform through the matrix lambda. However, we can see if this is true, the following statement is also true due to the chain rule of derivatives, that the partial derivative with respect to the coordinate mu, or the Jacobian transformation rule, the partial derivative with respect to some coordinate x mu goes to del upon del x primed mu, and that can be shown transforms like the previous partial derivatives, but this time with a new matrix lambda inverse. So coordinate differentials themselves could have been written in terms of their older versions through matrix lambda. Coordinate derivatives can be written in terms of their previous version through a matrix lambda inverse. So that is what one can trivially find out from these, that you can write down from Jacobian transformation such a thing is possible. So coordinate differentials themselves transform with lambda, coordinate derivatives transform with lambda inverse. Okay, and you can see that in coordinate differentials, the indexes appear in the upper side, while the coordinate derivatives index appear in the lower side. So this is the hand rule, a thumb rule which we can use, that whatever has an upper index will transform with matrix lambda, whatever has a lower index will transform with a matrix lambda inverse, where lambda inverse will be the inverse matrix of this. Okay, so let us see one example. Suppose there is a upper index object p mu. What should be its new version in a new inertial frame? It should be p primed mu, and since it has an upper index, it should transform with matrix lambda multiplication. Okay. Similarly, if there is a 2-index object which has 2 upper index, call it p, mu, nu, each upper index will bring in 1 lambda. So in a new inertial frame, p primed mu nu will be obtainable from the previous p through 2 lambda multiplications. So see, in this 1-index object, the index became the first index of the matrix, the second index got summed over, nu was getting summed over. Here also in the 2-index object, the upper 2 indices become the upper 2 indices of the 2 matrices, while the lower indices of the 2 matrices get summed over. So this is how a general rule will follow. As many upper indices are there, those many lambdas will appear in the game, in the transformation, and all the lower indices of the lambda will get summed over. Okay. The similar kind of thing is true for lower index objects as well. We have seen that coordinate derivatives transform with inverses of lambda. So all lower index objects transform with a lambda inverse matrix. And this time the upper index gets summed over. Previously the lower index was getting summed over and upper index remained intact. This time the lower index will remain intact and upper indices will be summed over, and the matrix will be replaced by lambda inverse. Similarly, for more than one lower index object, those many lambda inverses will appear, and upper indices of all of them will get summed over, and the lower indices will remain intact. Okay, so this is the general prescription of transforming upper index objects or lower index objects. Upper index object transform with matrix lambda, lower index objects transform with matrix lambda inverses. All right. So now we have this at our hand, then we can try to find out if there are invariant quantities around or not, which was our goal to start with. So let us look at this first demand which we had. This quantity I am going to define as c square times some invariant d tau square. So this quantity I am just right now proposing, which is just c square dt square minus dx square minus dy square minus dz square. So this is the quantity I am looking at. Let us find out what happens in the primed frame. In the primed frame, it will become c square remains c because it is a constant. D tau should become d tau prime, which is this, and its appearance should be c squared dt primed square minus dx primed square minus dy primed square minus dz primed square. And I know under Lorentz transformation how do these quantities transform. First of all, dy and dz primes do not transform at all, so they will just become plain and simple dy square and dz square. Dx primed is equal to this 1 over square root of 1 minus v square by c square times dx minus v by c and c dt. This is the rule for dx, which can be obtainable either from this row, or the boxed equation which we had written previously. From here you can take the derivative on both sides. You will get dx primed is equal to dx minus vc times c dt. So that is what we have written over here, that dx primed is this quantity. Similarly, dt primed is this quantity. C times dt primed is this quantity. Now we, in the new frame, this quantity d tau primed square is written in this form. We can open up those brackets and try to collect things. So you will see that opening this bracket will give rise to these three terms: a square plus b square minus 2ab. Opening this bracket will give again rise to three terms: a square plus b square minus 2ab, and then dy square and dz square. Now it so happens you can combine various. First of all, you can see that these cross terms between dt and dx exactly cancel each other, and when you combine terms like dt square from here and here and terms like dx square, these two, you will get exact cancellations of factors, and you will get just c square dt square and dx square. So you see, if I started with a primed frame, I got the thing in the unprimed frame, which is the same. That means d tau primes is also equal to d tau. Not only c is same across all frame, d taus are also same across all frame. D tau is not a constant, but it is invariant. Its value may change, but not across frames. So sometimes for some dx, dt, dy and dz, that d tau would be, let us say, 7 units. Then all observers, all inertial frames will say that it is 7 units. They will not agree on what is dt. They will not agree on what is dx or dy or dz. They will say that they will have their own dt prime, dx prime. But they all agree that this combination of dt, dx, dy and dz, that is invariant. So this is an invariant scalar. So we can use d tau as a d lambda. Previously we were looking for a lambda parameter which was invariant, right, in order to define velocities and whatnot. Now we have this quantity d lambda which can play the role of, we have this quantity d tau which can play the role of d lambda. So we can define the velocities and accelerations as derivative with respect to this parameter d tau, which is an invariant parameter. It is not a constant parameter, but it is an invariant parameter. And this is given a name, proper time. So now we have a velocity which is defined with respect to the derivative of with respect to proper time. So that is given a name, proper velocity. Similarly, acceleration can be also obtained from the double derivative of the positions, the space-time positions, with respect to proper time. So that would be proper acceleration. Similarly, we can search for other invariant quantities. You can prove using the transformation relations of dt, dx, dy and dz. Just like previously, this combination was an invariant combination and it gave you an invariant scalar. This time, we don't. There is a holiday tomorrow. So tomorrow is holiday, so we are not. Okay. So just like previously, here should be a plus sign. So just like c, this combination c squared dt square minus dx square minus dy square dz square was invariant, then we can prove from the similar logic of transformations that this particular combination of coordinate differential derivatives is also invariant. This is an exercise for you. You can prove along the same lines that this operator does not, this combination does not change. So it is invariant, but it is not an invariant number or invariant scalar. This is invariant operator. It has to act on some function to give you a number. So therefore I cannot use this as a d lambda because it is not a number yet. This is, the previous one d tau was a number. So that's why I could use that with respect to the, as a mimic for lambda. I cannot use this because lambda is not obtainable yet unless it acts on something. But still, it is some invariant operator. That means acting on some function, it will give a number. Acting on a scalar, it will give a number which will be agreed upon by all inertial frames. More importantly, if I take a lower index object mu nu, I know that it has to transform through 2 lambda inverses, because the rule we have set up is that anything has a lower index, it will transform with as many lambda inverses. And the transformation laws which we had written was like this. So similarly, eta mu nu, if I define, should be eta mu nu primed, which will, in which alpha will come about. Alpha would be the sum index which is upper, mu here, then there is a beta and lambda inverse here, nu here and beta, and eta alpha beta. This is how any lower index tensor will transform. Now if I give you a specific tensor whose properties are these, that its 0 0 component is -1, all other diagonal components are 1, 0 on all off diagonal components are 0. That means if I want to write it in terms of matrix form, it is -1 1 1 1 and all other quantities are 0. Then using this transformation properties like here, one can prove that this quantity eta mu nu also does not change under Lorentz transformation. So this is one of the special two-index object which does not change. So eta primed mu nu is also the same set, that it is -1 1 1 1 and all other entries are 0. This happens only for this special two rank object. Any other two rank object might not do this. So this is a special invariant tensor. Okay. So this is given a name metric tensor. So we have learnt about three invariant objects. One was an invariant scalar, which gives you a number which is universally agreed upon. Then there is an invariant operator which acts on a scalar and then gives you a number which is universally agreed upon. And then there is a tensor whose components are universally agreed upon. Okay, fine. So out of these invariant quantities, and apart from that, speed of light is also one of the invariant quantities, but it is a constant quantity as well. So we can construct various, we have seen that examples of various invariant quantities. Now we can look at what is the prescription of getting invariant quantities. So for that, it is suggestible to look at the structure of the matrix transformation. The transformation which we wrote down, lambda. Remember, the lambda matrix was what? Lambda matrix was a block diagonal matrix. Here was something, here was something, then nothing in this block, nothing in this block, and identity matrix in this block. Now you pay the close attention to this, the upper 2 cross 2 dimensional block. This is a very peculiar matrix. The same quantity appear in the diagonal and same quantity appear in the off diagonal, and more so, diagonals multiplied minus off diagonal multiplied is 1. You can verify that this square, this times that minus that times that is 1. That means you have a structure like cos hyperbolic alphas for some alpha parameter in the diagonal and sine hyperbolic alphas for some alpha parameter in the off diagonal, such that diagonal multiplied minus off diagonal multiplied are 1. So this is a lambda matrix. The inverse of that matrix would be just alpha going to minus alpha. So this becomes the inverse matrix. It's minus sine alpha, sine hyperbolic alpha and minus sine hyperbolic alpha. So therefore, we have a structure which is something called a group theoretic structure, that we have association between two different parameters. Like if I take one lambda with a parameter alpha, multiply with another lambda with a parameter alpha prime, I will get a resultant matrix which is also a lambda like this kind of matrix with parameter alpha replaced by alpha plus alpha prime. So this is the association law. Then we have an inverses. I know that for a given alpha, I have a minus alpha which is inverse of the element, and then alpha is equal to 0 is identity matrix. So this makes it a group. People familiar with a bit of group theory would find it useful that this Lorentz transformations constitute a group, a continuous group. Continuous in the sense alpha can take any value. Just like velocity v could have taken any continuous value, alpha can take any continuous value. Okay. So this is how this group elements, so the different groups, different group elements are marked by different choices of alpha. Now using these, one can further look at, as we have already seen, that the eta mu nu under the action of this group, which is just another name of transforming through lambda inverse matrices, does not change. And we have already summarized that any object which has two lower indices would be given a name rank 0 to tensor. Anything with upper index will be given rank 20 or 10 tensor. So upper index objects are in this side, lower index objects are in that side. So for example, eta mu nu does not have any upper index, so it will have upper index count 0 and has two lower indices, so it has a lower index count 0. So therefore it is a rank 0 to tensor. Similarly, dx mu has only one upper index, so its upper index count will be 1 and no lower index, so its lower index count will be 0. And I know that any upper index object transform with a lambda and lower index objects transform with as many lambda inverses as the lower index count is. So therefore, suppose I have a quantity which is one object with two lower indices and one object with one upper index. So then I have a three index object, one upper index and two lower indices. So then it will be called rank 1-2 tensor because it has one upper index, so upper index count will be 1, two lower index, then its lower indices count is 2. However, there is a special case in which I do not just put eta mu nu and v alpha side by side. I take this alpha, put it to value nu and then sum it over. This operation is called contraction. So previously here I had put alpha to be any value and nu could have taken any value, mu could have taken any value. So these are independent. So then it became a 3 index object. However, if I do not allow alpha and nu to take any values independently, but I force that alpha will take only those values which nu takes, and then I sum over the nu, then this operation is called contraction. And you can prove from here that if this transform with 2 lambda inverses and this transform with 1 lambda, and I have forced that the lower index of this and upper index of that have to be the same and summed over, that effectively multiplies these two matrices. And therefore this will become identity and resulting quantity will just transform with 1 lambda matrix. Therefore, if I just put these two objects eta mu nu and v alpha side by side, I get a rank 1-2 tensor. But instead of putting side by side, I contract their indices, then I lose one pair of lambda inverse and lambda, and the resultant thing will transform with only 1 lambda. So therefore it would be the resultant thing will transform with only 1 lambda inverse. So it has 2 lambda inverses here and 1 lambda. So these two got cancelled out under contraction. The resultant thing is transforming only with 1 lambda inverse. So this, therefore, the resultant quantity will be a rank 0-1 tensor. Okay. Similarly, if I take one lower rank index tensor and one upper rank index tensor and contract them, do not just put them side by side. The lower index of this and upper index of this has to be the same and they are summed over, then they are contracted. Then you can prove that this transform with 1 lambda inverse, this transform with 1 lambda, lower index of this and upper index of that are being summed over. That means it is matrix multiplication and this becomes identity. That means nothing is left over. This becomes a rank 0-0 tensor. No lambda is left out after this operation. So it is a rank 0-0 tensor. That means it does not change with any lambda under Lorentz transformation. So a rank 0-0 tensor is also an invariant or a scalar. That is what we were looking for, right? So those quantities which do not change under Lorentz transformations are rank 0-0 tensor. And rank 0-0 tensors can be obtained from contracting a lower index object with an upper index object, or any rank 2 upper index object with a rank 2 lower index object. If you contract both the indices, you will get a scalar. Okay, so this is one example. Again the same thing, that one lower index object v prime lower mu and v primed upper mu. This is the, let us say, velocity velocity dx primed upon d tau is dx prime mu upon d tau is the velocity for space-time velocity as seen in the prime frame. This v lower mu is obtainable from contracting dx primed mu upon d tau with, so this should be mu, with eta mu nu. So as we saw that if I contract the lower index of eta mu nu with the upper index of v, I will get a lower index object. So here, therefore, this v primed mu is just the contraction of the upper v prime mu with eta mu nu. So v lower prime mu is contraction eta mu nu and v prime mu. So if I take a velocity, for vector in any frame and contract it with its lowered version, which is, this is the lowered version, then the resultant quantity will be an invariant rank 0, 0 tensor, and you can prove that its value is the same as if it is in the unprimed coordinates. So this is a rank 0, 0 tensor, or a vector contracted with itself is an invariant quantity. That is like a magnitude of a vector. This time I am not doing just plain sum over all the components dt square plus dx square plus dy square plus dz square. I am doing a contraction. A contraction brings in eta mu nu, and that eta mu nu, if you remember, had a -1 along one of the diagonals. So therefore it is not just plain summing over, one of the element is picking up a negative sign. So this is a contraction. So this is how, through contraction of various vectors, we can generate invariant quantities, rank 0, 0 tensor. You take any vector, make its lowered version by contracting it with eta mu nu, and then take the lower index object and upper index object, contract them together. That would be an invariant. So this is how we would be able to constitute various invariant quantities, and using that we can find out invariant laws, invariant physics laws, which would be useful for writing correct physical laws which are respected under Lorentz transformations. And once we are comfortable with that, we will try to write down the similar kind of things for quantum theories. What laws of quantum theories are invariant under Lorentz transformations? So I stop over here for this lecture. In the next lecture, we will build upon from here. So now that we know what are the invariant quantities, we will try to how to get the invariant quantities. Then we will try to use some invariant quantities to write down good laws and good relations. Okay, so I stop over here.